The way you are staring at the board really scares me. I understand that few things were not clear. Questions? If any part of it, or does it seem like too magical? How did someone come up with the trick or something? Is that that I understand, right? So there were so actually the u theta part. Suyash already guessed, so that was not surprising. I would say the third idea is the main idea, which is kind of magic. You write it as a matrix. 0 goes to cos theta 0 plus sin theta 1. What will 1 go to? Minus sin theta 0 plus cos theta 1. What is this vector? What is the projection on 0? Minus okay, I have given you action on the basis. You can write the action of the matrix. Okay, so probably this kind of gate was new. I was talking about Hadamard, I was talking about Pauli, right? This kind of a matrix seems new to you. This kind of a gate seems new to you. But what I want you to realize is what are unitary operators. Okay, so let me take 2 minutes to explain to you what unitary operators are. Unitary operators are analog of, in case of real numbers, what will the analog of unitary? U transpose U equal to identity. These are called orthonormal matrices, right? Orthogonal matrices. They are called orthogonal matrices, but the columns are orthonormal. So what does orthogonal matrix do? It does a change of basis, right? What is a change of basis? It is saying that what is a change of basis which takes 0 to plus and 1 to minus? Rotate by 45 degree. But what is, do you know this matrix? Hadamard. It's the matrix which takes 0 to plus and 1 to minus. Correct? So any matrix which is taking u1 to v1, u2 to v2, u3 to v3, un to vn is basically a rotation. It's a unitary matrix which we already know, but it's basically a rotation. By pi by 4. By pi by 4. Right? Because other way to say it is two gates are equivalent if their action on basis is the same. What does Hadamard do? Rotates 0 by 45 degree, rotates 1 by 45 degree. Correct? What does, so then the action of the Hadamard is exactly the same as rotation on 0 and 1. So then they are the same gates. Correct? What about the matrix which rotates 0 by 45 degree but rotates 1 by, let's say, 22.5 degree? Is that a unitary? No, because you won't get an orthonormal basis. Right? These angles have to be equal if it has to become orthonormal basis, right? So the rotation picture is in 2 dimensions. I'm extending that rotation to n dimensions. It's basically taking any orthonormal basis into another orthonormal basis. So rotation is going from one orthonormal basis to another orthonormal basis. But this, you know, these are unitary matrices. Correct? In real matrices, if you read, orthogonal matrices are rotations in the real space. These are rotations in the complex space. That's all. Okay? So once you understand that, then instead of rotating this entire way, u theta will rotate here. Now u theta is kind of, yes.
So if we
no, that will not. Oh, you mean this way? No. Here.
0 goes to theta, but 1 goes to theta plus phi.
That's not preserving the angle between the two, right? So it will not be. Right.
Give a minus. Minus
But you did not mean pi plus theta.
1 will go to 1 say pi plus theta.
अच्छा यहाँ से pi plus theta. Okay.
It will be 90 degrees.
I understand what you are trying to do. You are trying to make one here.
Still orthogonal.
So U0 is here, U1 is here. So that these are perpendicular to each other, but there will be a phase which might be an or wait. This is also unitary.
Just rotate the 0 downwards and then do a split operation of 0 goes to 1 goes to.
Oh, sorry. Okay, yeah, you are right. So when I said unitaries, there is one more operation in unitary, the flip operation. That's also unitary. Flip, yeah. So that would be correct, right? So yeah. So this, right? So yeah. So okay. No, actually, not just mirroring. You put any diagonal matrix with complex coefficients. So that's clearly a unitary, right? So those are kind of trivial unitaries which we did not take into account, right? So you put e to the I theta 1, e to the I theta 2, e to the I theta 0, c. Correct? This is clearly a unitary. But yeah, you won't call it a rotation, right? So that modulo this trivial unitaries, everything is a rotation. Thank you for correcting me. Yes. Is that okay? So that will amount to, I think, plus minus 1 in the real case. All the eigenvalues have magnitude 1.
When you take the conjugate transpose, when you conjugate it close to t minus sin theta. Oh yeah, it's not Hermitian.
It's not Hermitian. I'm not saying it is Hermitian. It is unitary. Question. Thank you. Right. So this is clear. So in the real case, you are allowed this plus 1 minus 1 business. That changes to this kind of a matrix. Right. Modulo these, every unitary is a rotation. So, but then we don't have to worry about this. U theta is very, very simple. It is just a basic rotation without any of these complex coefficients attached to it. Okay. So we have done more difficult things first. Now let's do the easy thing. Okay. Here the bomb was resetting to 0. Now what should I do so that you reset to the initial state at the beginning of the lecture? Reset. Okay, where are we? Mach-Zehnder and Elitzur-Vaidman, right? These two you understand, correct? Now, let me phrase the question slightly differently. You look at these pictures, I want to differentiate between the two cases, right? But my difference is not really precise in the sense that yes, if I measure at D2, then clearly I know that I'm in this case, right? But if I measure D1, then I don't know, right? Instead of bomb, can I put something here? Can I put some other gate here so that I always measure D2 here? So bomb was a measurement, correct? With the bomb, obviously, I can distinguish it with high probability, but not always, right? So bomb was a device. If I measure at D2, I can distinguish between these two cases. But if I measure at D1, then I am lost. Then I don't know. I might be in this case or I might be in that case. Now I change the problem slightly. I say, forget about bomb. What gate can I put here so that I always measure my photon at D2? Wait, Shuyash, let others answer. And you just have to remember, why were we getting everything at D1? So let me phrase the question. Replace bomb with a gate so that photon gets to deep. Okay. And yeah, let me erase this so that you don't keep looking at the probability going to one case. We have reset it. Right? Okay. So we are now thinking of a very, very different problem. Using this Mach-Zehnder and Elitzur-Vaidman, we want to come up with a computational problem, Deutsch's problem. Okay. And I'm going to just show very, very simply from here, we will move to some very nice computational advantage. Okay. Yes.
So we know that let's say that the bomb there is constructive and destructive interference because of the difference of phase between the upper part and the lower part. So if at all we change the phase of the lower part by 180 degrees, that is pi, then the constructive and destructive interferences will flip.
Will flip. Very nice. Right? So what was happening? There was constructive interference here, there was destructive interference here. If I put a phase of -1 or pi, then destructive interference will happen here, constructive interference will happen here. Right? So in some sense, that's putting like a Z gate. Okay? Correct? So this will be a controlled Z. Control Z. Because on 0, I don't put a phase, on 1, I put a phase. Right? But anyway, so you see that, so let me just keep the physical apparatus in mind. Right? So in this case, I am getting D1. Correct? You can always assume photon from here. If I put a phase gate here, so phase shift, what is it called? Optically, there is some device which changes the phase, right? Okay, phase gate. I hear dielectric material, I go into a shock. So let's not go to dielectric material, but something, some physical device which applies a phase. Correct? Then what is happening? Yeah, I should. What should I observe now? By our physics intuition, and you can check it, by the way. You can do the calculations by yourself. What will happen? What will happen? I will measure at D2. I put phase gate at both. Goes back to D1. Right? Whatever phase difference was here, same phase difference I will obtain here. I put a phase at the top. Correct? Remember our notation? This was the 0 branch, this was the 1 branch. Okay? Now, if the phase gate is at both or none, I can distinguish this with the case when phase gate is exactly at one place. Right? So let's say if F0 is 0, okay, again, I wanted a computational problem, right? So I'm creating a computation, I am creating a function, right? Where what am I saying? If I'm putting a phase gate here at the bottom, I will say the function value here is 1. If I'm not putting a phase gate here, I will say that my function value is 0. Similarly so this will be function value at 0, this will be the function value at. So if you are confused, let me say function value at top, function value at bottom. Okay, function value at top, if it is 0, I will not put a phase gate at the top. So whether there is a phase gate or not a phase gate depends on my function value. Other way to say it is someone will give me the function value. Using that I will have a switch so that the phase gate will rotate and come in the path or something. Okay. Now what has happened? What are the two cases which I have distinguished? What are the two cases which I have distinguished? When both the phase gates were there, or zero phase gate, 0. So both or none compared to exactly 1. Correct? Right? What have I computed? What function have I computed? Do you know this function where if exactly 1 is there, then you get 1? I have computed okay, and now you have to take some physics intuition here. We will convert it into a circuit, okay, and then it will be ultra clear. But remember, even though you are putting a phase gate here or there, so let's say this is the device which is hiding my function values. Okay, I have looked at this box just once. I have shot just one photon here, right? So I have looked at this box just once and I am able to answer this XOR. Classically, if I had to figure out this thing for a function, I have to ask this box at least 2 questions. You have to send 2 photons. You have to look at it twice. Otherwise, there is no way classically you can compute this XOR. Quantumly, you have just shot 1 photon. You have looked at this box. It will have all the function values, I don't care. but you have shot just one photon. And you have gotten this value. You haven't gotten both the values, by the way. And there is no way you can do it. Quantum information prohibits you from getting both these values. You will never get both these values. It's not like we have seen both things in parallel. You have to understand this. With one photon, you can only calculate one bit of information. Luckily, it's the information which we needed, which is not possible classically. This is going to be your Deutsch's problem. Okay, this is the intuition. So you notice that we have calculated this value just by shooting one photon, right? Now, let me give you the computational problem. Let me write the Deutsch problem, then you will see the equivalence. Okay. Okay, so again, reset. Let's just look at this problem. We will draw the analogies very, very soon. I think the analogies are quite clear now, but let's not get into that. So, what is the Deutsch problem? You have a function from 0, 1 to 0. Okay, that means there is f0, there is f1. There are two numbers which are hidden inside an oracle, inside a black box, or whatever you want to say, right? If you are Matrix fan, then you will probably call it. How many people have seen Matrix? Okay. At our time, you cannot be an engineer without seeing Matrix. So watch Matrix movie. Okay. So oracle basically means you don't know the workings of it computationally, but it will work. It is like a subroutine. Okay, but you're not allowed to look inside it. So this is an oracle which hides this function. So you give it b, it will answer f of b. Okay, your job is not to compute f. F is given to you as an oracle. Question is it? In how many queries can you find f0 XOR f1? Or other way to say it, you have to find out whether f0 is equal to f1 or f0 not equal to f1. That's same as finding its parity, right? If parity is 0, that means they are same. If the parity is 1, that means they are different. Correct? So you are asking whether f0 is equal to f1 or not. Clearly, so suppose every time you ask the oracle, it will charge you $1 million. Okay? Now classically, how much money do you have to spend? 2 million. There is no way in $1 million you can compute whether f0 is not equal to f1 or not. Correct? In $1 million, assuming quantum oracle is at the same cost as the classical oracle, we will do it just with one query. So with one query to this oracle, one photon shooting, we will figure out f0 XOR f1. And it is going to be this circuit. Right? What is this circuit? Header, apply the function value, header, measure. Okay, I just have to explain what does it mean applying the function, right? So this phase gate, when you apply it, this changes. What is it doing as a function? Sounds good? And things will work out. So, okay. So, observation 1. There is no doubt about it. Okay? Questions? No? right? Now, analogy with Mach-Zehnder, need one query okay. So obviously I can't give this oracle to my quantum circuit. Why? Why can't I give this to my quantum circuit? No, but suppose this is my action. On cat 0, I will get cat F0. On 1, I will get cat F1. No, input, output, both are 1 bit. Exactly. If F0 is equal to F1, is this unitary? No, both 0 and 1 both are going to the same value. So this is not a reversible gate. Right? So I have to make it reversible. And we have seen this a lot of times in the discussion of quantum circuit. There is a way in which every classical circuit can be made reversible. Right? And if you remember, there was a standard trick to it. How did we compute AND? So let's say do you remember we did that? What was here? How did we compute AND? We did this binary addition, remember? We needed for the carry, we needed AND. How did we compute AND? What gate did we apply? C0. What does it do? Right? What is CC0? If I change it to CC0, right? It computes AND as an XOR in the ancilla bit. Correct? And in general, when you take a reversible circuit, you take a classical circuit, when you convert it reversibly, the idea is you just compute this function in the ancilla to keep it reversible. Right? You remember half adder? We did the same trick there. Right? So this is not a new trick to you. This is how you make things reversible. In the half adder also, we had A, B, and then we had 2 bits, one for answer, one for carry. Correct? Right? So again, in all these, the idea is that when you take a reversible circuit, when you convert it into, when you take a classical circuit, you convert into a reversible circuit, the value is computed like this. Okay, this is nothing magic. This is not where I am cheating. This is not where I am giving more power to the quantum oracle. You can give this circuit to the classical oracle. Even then, you will need 2 queries. This, if you have this oracle, you can convert into this. If you have this, you can convert into this without any addition queries. Right? So it's not like this oracle is much more powerful than this oracle. It's just that quantumly, I have to give something reversible. Okay? And another justification is that using this oracle, you can get at most 1 bit of information from one query. This is called Holevau's theorem. It is known. So what I'm trying to say is that it is justified to give this as the quantum oracle, as well as classical oracle. So you can, in the Deutsch's problem, the oracle was specified like this. You can give this oracle. Classically also, quantumly also. It's very clear classically, you will need 2 queries. But quantumly, you are allowed to give superpositions here, not just classical bits, obviously, because it's a quantum oracle. Okay, so what we will see this will give me answers. This will actually give me and if you notice, this is exactly the same as this picture with the phase replaced by the oracle. So the reason why we are able to do this, the reason why we are able to come up with this circuit is because it is just replacing Mach-Zehnder. And we have seen Mach-Zehnder converting into circuit. We have done it 1,000 amount of times. Okay, so again, if you look at Mach-Zehnder, if I put a phase here, I can differentiate from the original phase. If I just put a phase here, again, I will detect only at D2. If I put phase at both the places, I will once again detect at D1, right? So if I encode presence of phases as 2 bits, I can calculate whether those bits are equal or not just by shooting 1 photon. That's what Mach-Zehnder is doing. And that I can convert it into Deutsch's problem. That's exactly the Deutsch's problem. This is the computational advantage. Okay, so this was the intuition. We will again make the circuit. You will again see constructive-destructive interference exactly as it happened in the Mach-Zehnder next time. Okay, thank you.